In the very first second of its existence, the universe is dominated by particle physics. Right at the beginning of this brief second, the entire energy mass content of the universe is a quark-gluon plasma that is illustrated in this sketch. The diagram shows the transition from this quark-gluon plasma to elementary particles like hadrons. Hadrons are protons or neutrons. This is understood to have happened like a thermodynamic phase transition. In this diagram, on the y-axis, temperature, which is the energy, the heat content of the universe during that 1 second, is plotted as a function of matter density, Barian density. Immediately after the Big Bang, only quarks and gluons can exist. They are illustrated here as green, blue and red balls, that's the quarks, and whizzing between them as white shadows are the gluons. This artist's conception of the quark-gluon plasma then changes as both temperature and matter density decrease. The plasma condensates, and out of this condensation, hadrons arise, protons and neutrons. They are shown in the bottom left corner as the combination of 3 quarks held together by gluons, forming a hadron each. The transition expected from the quark-gluon plasma to hadrons can be probed in particle accelerators such as LHC and RHIC. LHC, the Large Hadron Collider, is located at CERN in Geneva, and RHIC, the Relativistic Heavy Ion Collider, is on Long Island in New York. In these large laboratory experiments, the matter density is relatively low. However, the temperature required to permit a phase transition between quark-gluon plasma and condensed hadrons can be achieved. The situation at the other extreme, relatively low temperature, however high matter density, is believed to occur in neutron stars. That's indicated on the bottom right. In this presentation, I want to discuss the conditions and the particles involved in this first second of the existence of our universe. After the decoupling of electromagnetic radiation from matter at about 380,000 years after the Big Bang, the time-temperature relationship of the universe can be inferred from Planck's radiation law. This is illustrated here at the top left, where the intensity of the radiation in the universe is plotted as a function of the wavelength of the radiation. Indicated also are the associated temperatures. At the decoupling, the temperature was about 3000 Kelvin. This temperature has since then decayed to 2.7 Kelvin, which is the value of it today. The integral under the curve, which is shown shaded, corresponds to the energy content of the universe that is carried by radiation. It can be calculated using Stefan Boltzmann's law, which is P, which is the power of that radiation, this total radiation, which is given by sigma, the Stefan Boltzmann constant, times A, the area of emission, times the temperature to the power of 4. It is clear that this relation permits a direct conversion between the energy content and the temperature of the universe. This equation, in addition to the Friedmann equations from general relativity, permit us to go back in time and study the conditions of the universe before today. Before 380,000 years, the time-temperature relationship of the universe cannot be inferred from Planck's radiation law. Instead, the relationship shown here is used. Without derivation, we note that for this early period of the universe, the time, its age, is equal to 4 times 10 to the 20 seconds times Kelvin squared divided by temperature squared given in Kelvin. Let us apply this relationship between time and temperature to the first second of the universe. Let us see what typical energy we obtain at that time of its history. In order to achieve this, we have to rearrange the equation so that the temperature is given as the square root of 4 times 10 to the 20 seconds times k squared divided by time, and we substitute here with 1 second. This gives us a temperature of 2 times 10 to the 10 Kelvin. Multiplying this now with Boltzmann's constant Kb, we obtain an energy of 2 times 10 to the minus 13 joules. The unit joules for energy is inconvenient in microscopic physics, so that we convert to electron volts and obtain 10 to the 6 electron volts, and the typical energy of the universe at the end of 1 second. 10 to the 6 electron volts, 1 mega electron volts, is the typical excitation energy of atomic nuclei. This tells us that only before 1 second the particle physics dominates the universe. In the few minutes afterwards, it is instead dominated by nuclear physics. Because of its importance, the conversion from joules into electron volts is illustrated inside the blue frame. 1 electron volt is equal to 1.6 times 10 to the minus 19 times 1 coulomb times 1 volt, which is equal to 1.6 times 10 to the minus 19 times 1 joule. Rearranging gives us that 1 joule is equal to 1 electron volt divided by 1.6 times 10 to the minus 19, which is the conversion formula. This view graph shows the history of the universe, indicating on the left important events during its history, and on the right the discipline of physics that dominated. After the Planck epoch, the grand unification transition occurs, where inflation and baryogenesis take place. This is followed by the era of quark-gluon plasma, where the electron-weak phase transition occurs at a typical temperature expressed in energy units of 10 to the 3 gigaelectron volts and at a time of 10 to the minus 11 seconds. This is followed by the quark-gluon phase transition to baryons, which spells the end of the era of particle physics. This phase transition occurs at a typical temperature below 1 gigaelectron volts expressed in energy units, which occurs at a time of 10 to the minus 6 seconds. After about 1 second, nuclear physics dominates and Big Bang nucleosynthesis starts. The modern universe outside stars is dominated by atomic physics and solid-state physics on planets like Earth. All these disciplines of physics have quantum phenomena and can only be fully understood with a sound understanding of quantum mechanics. During the 1 second of particle physics in the history of the universe, the forces split into their 4 manifestations: gravitation, weak, electromagnetic, and strong force. Leptons, as fundamental particles, that's electrons, muons, and taus, and neutrinos, are generated in leptogenesis. Quarks are created that then form hadrons and mesons. And at about 1 microsecond, matter and antimatter annihilate. This is still very poorly understood. However, there must have been more matter than antimatter, because the modern universe is dominated by matter. The apparent matter-antimatter asymmetry is still a puzzling aspect of Big Bang cosmology. From experiments since 1932 we know that both matter and antimatter exist. A proton and an antiproton, p bar, annihilate when they are close. The same happens to an electron, E-, and a positron, E+, when they meet. In fact, this effect is taken advantage of in medical PET scanning, PET scanning, that one can encounter in a modern hospital. It's a powerful diagnostic technique that permits the detection of cancerous tumors. Since the standard model of particle physics predicts equal amounts of matter and antimatter, the question why matter dominates is still an unsolved problem. Why is there matter now? We don't know. All matter-antimatter pairs would have annihilated at 10 to the minus 6 seconds if matter and antimatter had been symmetric, and the world as we know it would not exist. The existence of antimatter, of antiparticles, was first predicted by relativistic quantum theory by Dirac in 1928. QED, quantum electrodynamics, suggests that energy is not just positive but can also be negative. This is illustrated by the sketch at the bottom. Zero energy is indicated by a dashed line, and above it we have positive energy states for particles. Below it, indicated, are negative energy states of particles. Those states are, however, filled. If a photon puts energy into this continuum of filled states, a particle is promoted into the positive energy regime. This is shown here for electrons. The excitation leaves behind a hole in the continuum, which is interpreted as the antiparticle, in this case as the positron. In order to generate a positron-electron pair, a photon energy of at least 1022 keV is necessary. The creation of more massive particle-antiparticle pairs, like the proton and the antiproton, requires photons of even higher energies. Extensions of this Dirac theory from 1928 have been quite successful, since they explain the production of matter-antimatter pairs and also the annihilation of such pairs. The few holes in the negative energy continuum fill quickly, which is consistent with the observed short lifetime of antiparticles. This model is valid for all types of particles, with a few important exceptions like the photon. PET scanning, positron emission tomography scanning, employs a radioisotope that is injected into the patient and, due to attachment to a biomolecule, seeks out tumorous cancers in the body. The radioactive beta decay of the isotope, once it has been incorporated into the tumor, creates a positron, which very quickly annihilates with a nearby electron. As a result, two photons, gamma-ray photons, are created that have the same energy, and importantly, they are emitted back-to-back at 180 degrees to each other. The energy of each photon is 511 keV, exactly half the energy of 1022 keV that is required to create a positron-electron pair. The photons can thus be identified via their energy, and if a sufficient number of photon pairs are detected in all directions, the center of radiation of these pairs can be identified. This is where the tumor can be suspected. The first observation of antiparticles, namely positrons, with the cloud chamber, was carried out by Carl Anderson in 1932, 4 years after Paul Dirac's prediction. In this experiment he placed a thick piece of lead, an illustration is shown on the right, inside a cloud chamber. A cloud chamber contains a saturated vapor that can be triggered to condensate if nucleation centers are provided. The track of ionizing particles, such as electrons, provides such nucleation centers. A cloud chamber thus makes tracks of charged particles visible. Anderson bombarded the lead with gamma rays with energies in excess of 1022 keV, and he observed on the other side that there are two types of tracks bending downward and tracks bending upward. The tracks bending downward he could easily identify as those of electrons. The curvature of the tracks was caused by a magnetic field that was penetrating through the cloud chamber. In order for electrons to be bent downward on a circular path, the magnetic field has to point into the plane. Interestingly, tracks with the same curvature, however bending upward, were also observed. That could only be explained if particles were present that have the same mass as the electron but the opposite charge. Anderson concluded that those particles, called positrons, are the antiparticles of the electron. The electron is a lepton. Apart from the electron, there are two more leptons, the muon and the tau. They might be imagined as fat electrons. Leptons are fundamental particles because they are point-like, they don't have a defined radius, the radius is infinitely small, and they cannot be divided. Leptons have a negative charge and they all have antiparticles. The electron has the positron as its antiparticle, the muon has the mu plus as its antiparticle, and the tau has the tau plus as its antiparticle. Leptons were produced in the first second after the Big Bang, in the same way as in the experiment demonstrated by Carl Anderson. A high-energy photon, for the electron at least 1022 keV comes in, and in the presence of a baryon, for example a proton, which absorbs the momentum as a recoil and triggers the pair production, the matter-antimatter pair, the electron-positron pair, is generated. The same process can create a muon and its antiparticle and a tau lepton and its antiparticle. There are 3 leptons in the standard model of particle physics, and for reasons I don't want to go into now, each of them also has a neutrino. There is an electron neutrino, nu e, a muon neutrino, nu mu, and a tau neutrino, nu tau. Associated with each antiparticle is an antineutrino, the anti-nu electron, the anti-nu mu, and the anti-nu tau. Compared to other fundamental particles, the 3 leptons tend to be small and light. They do not feel the strong interaction which characterizes them. They have spin 1/2, which makes them fermions. This means leptons, like any fermion, adhere to the Pauli principle. They are truly fundamental particles. The counterpart of the leptons are the hadrons. These are all fundamental particles that are not leptons, and that means they do feel the strong interaction. Hadrons are made up out of quarks. They have, in contrast to the leptons, a finite size. They are not point particles. There are 2 types of hadrons: mesons, which consist of 2 quarks, and baryons, which consist of 3 quarks. In order to make a meson, a quark has to be combined with an antiquark that doesn't correspond. Since there are 6 quarks, up, down, strange, charmed, bottom, and top, for example, its strange quark has to be combined with the anti-charm quark in order to make a meson. Baryons, such as the proton and the neutron, are made of 3 quarks, and in this case all the quarks are either matter or antimatter. For example, the proton consists of 2 up quarks and 1 down quark. Since quarks carry charge, either plus 2/3 of an elementary charge or minus 1/3 of an elementary charge, the combination of quarks leads to charged particles or possible neutral particles if the quark charges balance to 0 Coulomb. We think that quarks, together with gluons, the particles that mediate the interaction between quarks, the strong force, were present right after the Big Bang, as part of the fireball originating from the Big Bang. However, at about 10 to the minus 35 seconds, a phase transition occurred, similar to what we have in thermodynamics when vapor condensates to form droplets of liquid water. This is illustrated with the phase diagram on the right. At 10 to the power of minus 35 seconds, the typical particle energy, kBt, of particles in the fireball was larger than 1 gigaelectronvolts. However, the expansion of the universe, of that fireball, caused the temperature and also the matter density and pressure of that fireball to decrease. This caused a phase transition where a quark and an antiquark could condensate to combine to a meson, and 3 quarks could combine to form baryons, such as protons and neutrons. Since we are dominantly made out of protons and neutrons, they make up more than 99% of our mass as humans. Let's discuss the quark structure of protons and neutrons as an example. Both the proton and the neutron are baryons. That means they consist of 3 quarks. The proton has 2 up quarks and 1 down quark, and what I've drawn here as springs are meant to be the gluons that mediate the strong force that keeps those 3 quarks together. In contrast, the neutron is made up of 2 down quarks and an up quark. It can be readily seen that produces the correct charges, namely 1 elementary charge positive for the proton and 0 charge for the neutron. The 2 up quarks of the proton contribute plus 2/3 of a charge, which is 1.333 Coulomb. If you then subtract 1/3 of an elementary charge due to the down quark, you obtain the familiar plus 1 elementary charge for the proton. In the case of the neutron, the plus 2/3 charge of the up quark is balanced by 2 negative 1/3 charges of the down quarks, giving a net 0 charge of the neutron. By adding the respective quark masses and considering the strong interaction between them, the proton mass turns out to be 938.3 MeV per c squared, and the neutron mass is 939.6 MeV on c squared. It is important to notice that the neutron mass is 1.3 MeV per c squared larger than the proton mass. It is therefore energetically favorable for the neutron to decay into a proton. Indeed, free neutrons decay with a half-life of 10.2 minutes. It is possible to create all fundamental particles in particle accelerators such as CERN in Geneva. However, in the atmosphere, also a considerable amount of particle physics takes place. For example, distant supernova explosions create highly energetic protons, cosmic rays, that travel over long distances through the universe until they interact in the atmosphere. Because of their energy, they smash nuclei there in spallation reactions, and a shower of subatomic particles is created. Such a shower is illustrated on the bottom left. A product of such a spallation reaction could be a meson, a pi plus. A pi plus is made up of an up quark and an anti-down quark. Because of the plus 2/3 charge of the up quark and the plus 1/3 charge of the anti-down quark, the total charge of the pi meson is 1 positive elementary charge. It has only a very short half-life of 2.6 times 10 to the minus 8 seconds. It is also not that heavy. Its mass is less than that of a proton or a neutron at 140 MeV per c squared. Like any meson, the pi plus decays into a lepton. In this case, a mu plus muon is created together with a nu mu neutrino. Since they travel close to the speed of light and experience time dilation, the lifetime of a muon is such that it can reach a laboratory on the ground. There it can be detected using scintillation detectors or cloud chambers. The photo on the top left shows an improvised cloud chamber, as it can be set up in a teaching laboratory. The metal base of a container is cooled down to well below freezing using dry ice. Inside the container, a saturated atmosphere is created using an organic solvent. Condensation of the saturated solvent vapor is triggered by the passage of an ionizing particle such as a muon. The photo on the right shows a track that has been observed with this device and may be interpreted as that of a muon. Compared to tracks that may be associated with background radiation, this track is straight and particularly long, which is characteristic for a muon passing through the device. This view graph gives an overview of the fundamental particles, the quarks and the leptons, shown on the right. There are 3 quarks, the up, the down, the charm, the strange, the top and the bottom, and the associated charges are indicated as well. Underneath, the 6 leptons that do not experience the strong force as it is mediated via the gluon. The electron, the mu and the tau are accompanied by an electron neutrino, a mu neutrino and a tau neutrino. Neutrinos are not charged, and the leptons have a negative elementary charge. The quarks experience all 4 fundamental forces: the strong force, the electromagnetic force, the weak force, and the gravitational force. Since electromagnetic and weak force can be described within the same theoretical framework, they are separated here only by a blue dashed line. Associated with each force within the standard model of particle physics are gauge bosons. This is the name for the particles that can be imagined to carry the force, to mediate the force between the fundamental particles. For the strong force we have the gluon as the mediator, for the electromagnetic force the photon. For the weak force we have 2 types of particles, the W and the Z boson, that mediate the weak force, and finally for gravitation we have the graviton. The graviton has not been fully explained, however the discovery of gravitational waves recently supports the idea that gravity is carried by a graviton particle. This slide gives the time and temperature scales over which the unified force is expected to have split into its 4 manifestations. First, at a time of 10 to the minus 35 seconds, gravitation split from the other 3 forces, which then split from each other at 10 to the minus 30 and 10 to the minus 10 seconds respectively. Ultimately, already before 1 second of the history of the universe had passed, all 4 forces were separated. The 4 fundamental forces can also be distinguished according to their relative strength and according to their range. The strong force might be considered to have a strength of 1, then the electromagnetic force is about 100 times weaker. The weak force is again weaker with a factor of 10 to the minus 5, and gravitation is very weak compared to the other 3 with a factor of 10 to the minus 39. The 2 more familiar interactions, electromagnetic and gravitational, have a long range. That means the Moon attracts Earth, Earth attracts the Moon. That's already a very large distance in the case of gravitation. However, the gravitational force extends much beyond that, in fact, into infinity. And the same is true for the electromagnetic force between charges. They may be separated by light years, but still they interact, at least weakly. In practice, however, many other charges are in between, so that these interactions over these large distances are of no significance. In contrast, both the strong and the weak force are short-ranged. The strong force only has a range of 1 femtometer. That's less than the diameter of a typical nucleus. The weak force has an even shorter range of 10 to the minus 3 femtometers. Therefore, both forces are only of significance inside atomic nuclei. The 3 strongest forces have been unified in a theory of the Standard Model. The full integration of the gravitational force into that theory has so far not been achieved. Within classical physics, no thought is spent on how forces actually operate. This is different in quantum electrodynamics, and it is achieved with so-called Feynman diagrams. A simple example is shown on the bottom left. It illustrates the repulsive interaction between 2 electrons. The diagrams are not meant to be geometric depictions, but they represent a mathematical formalism, a visual mathematical code that was developed in particular by Richard Feynman. In this case, a photon is emitted by 1 electron and mediates the repulsive interaction to the other electron. The second electron accepts the photon and is repelled. This mechanism is also often referred to as an exchange interaction. One might ask the question how it is possible for an electron to give up energy to create a photon that is then passed on to another electron. This sounds like a violation of energy conservation. Indeed, energy conservation is violated, however only briefly, and this is possible because of the quantum mechanical uncertainty principle, which was first introduced by Heisenberg. Heisenberg's uncertainty principle says that an uncertainty in energy, when multiplied with an uncertainty in time, is always greater equal to h on 4 pi, whereby h is Planck's action quantum. Applied to quantum electrodynamics, this means that the first electron can indeed give up some of its energy or mass to create a photon, if and only if the time it takes for the interaction to take place is reasonably short. This is illustrated on this view graph. Before the repulsive interaction between the two electrons, the total energy of the system is the mass of the two electrons, 1022 kilo electron volts. The shorter the time over which this interaction takes place, the more uncertain this energy can be. So during the interaction, the total energy of the system is somewhat larger than 1022 keV. Afterwards, after the interaction, when the photon has been absorbed again by the second electron, the combined energy of the system is again 1022 keV. So only briefly over the delta T of the interaction, energy conservation was violated, but still in agreement with the uncertainty principle. The brief violations of energy conservation as permitted by the uncertainty principle alert us to the importance of conservation laws. All conservation laws familiar from classical physics also apply within particle physics. Energy is conserved, momentum is conserved, angular momentum is conserved, and the electric charge is conserved. A number of additional conservation laws are added. Important among those are the conservation of Barian number and the conservation of lepton number. A baryon, such as a neutron, has a baryon number of +1, whereas the antineutron has a baryon number of -1. All other particles have 0 baryon number. The baryon numbers before and after an interaction or a reaction have to be equal. In the case of lepton number conservation, the same principle applies. An electron has a lepton number of +1, and the positron, its antiparticle, has a -1 lepton number. All other particles, like quarks, protons or neutrons, have 0 lepton number. An important example where lepton conservation plays a role is the decay of the free neutron, which is shown here. Before the reaction, the neutron, which is a baryon, has a lepton number 0. After the reaction, we have certainly a proton and an electron. So we have for the proton a lepton number 0 because it's a baryon, and for the electron we have a +1 lepton number. So we can see that the lepton numbers before and after the reaction are not the same. We start with 0 and now we've got +1. So therefore there has to be an additional particle, which is the anti-electron neutrino, which has a -1 lepton number because it's a lepton, but it's an anti-particle, therefore -1. The net lepton number on the right is therefore also 0. The decay of the free neutron proceeds with a half-life of 10.2 minutes, and since most of the neutrons were created right in the first second after the Big Bang, one would expect that after half an hour almost all of the neutrons would have decayed into protons. Since we and all other matter contain many neutrons, some neutrons must have been rescued, and in fact that occurred through Big Bang nucleosynthesis. Big Bang nucleosynthesis occurred over the first 3 minutes of the history of the universe. This view graph shows the free neutron decay that has a half-life of 10.2 minutes using the language of Feynman diagrams. The neutron, consisting of 2 down quarks and an up quark, converts into a proton, which is 2 up quarks and a down quark. This can happen if a down quark changes to an up quark. This conversion from down to up proceeds via the weak interaction, which is mediated by a W-, the gauge boson, one of the gauge bosons of the weak interaction. The W- takes away a negative charge so that the neutral charge of the neutron can convert to the positive charge of the proton. The W- then decays into an electron and its antineutrino. All reaction products are stable. The proton is stable, the electron and also the anti-electron neutrino are stable particles. Furthermore, lepton number is conserved because before the reaction the lepton number was 0, there was no lepton, and after the reaction we have an electron with a +1 lepton number and an antineutrino with a -1 lepton number, again giving us 0 lepton number.